Chapter 8. Electrostatics. Exercises pages 121 to 213. Exercises Q1.1, page 212. Choose the correct option. A parallel plate capacitor is charged and then isolated. The effect of increasing the plate separation on charge, potential, capacitance respectively are 1. Constant, decreases 2. Increases, decreases 3. Constant, increases 4. Constant, increases, decreases. Solution. Constant, decreases. Exercises Q1.2, page 212. Choose the correct option. A slab of material of dielectric constant K has the same area A as the plates of a parallel plate capacitor and has a thickness 3/4 d, where d is the separation of the plates. The change in capacitance when the slab is inserted between the plates is. Solution. Exercises Q1.3, page 212. Choose the correct option. Energy stored in a capacitor and dissipated during charging a capacitor bear a ratio 1, 1, 1, 2, 1, 2, 3, 2, 1, 4, 1, 3. Solution. 1, 1. Exercises Q1.4, page 212. Choose the correct option. Charge plus Q and Q are placed at points A and B respectively, which are distanced 2L apart. C is the midpoint of A and B. The work done in moving a charge plus Q from C to D, along the semicircle CD as shown in the figure below, is. Solution. Exercises Q1.5, page 121. Choose the correct answer. A parallel plate capacitor has circular plates of radius 8 cm and plate separation IM. What will be the charge on the plates if a potential difference of 100 V is applied across its plates? 1. 1.78 times 10 to 8 C2. 1.78 times 10 to 5 C3. 4.3 times 104 C4. 2 times 10 to 9 C. Solution. 1.78 times 10 to 8 C. Exercises Q2.1, page 212. Answer in brief. A charge Q is moved from a point A above a dipole of dipole moment P to a point B below the dipole in an equatorial plane without acceleration. Find the work done in this process. Solution. The equatorial plane of an electric dipole is an equipotential with V equals 0. Therefore, no work is done in moving a charge between 2 points in the equatorial plane of a dipole. Exercises Q2.2, page 212. Answer in brief. If the difference between the radii of the two spheres of a spherical capacitor is increased, state whether the capacitance will increase or decrease. Solution. The capacitance of a spherical capacitor is C equals, where A and B are the radii of the concentric inner and outer conducting shells. Hence, the capacitance decreases if the difference B, A is increased. Exercises Q2.3, page 212. Answer in brief. A metal plate is introduced between the plates of a charged parallel plate capacitor. What is its effect on the capacitance of the capacitor? Solution. Suppose the parallel plate capacitor has capacitance C0, plates of area A and separation D. Assume the metal sheet introduced has the same area A. Case 1, finite thickness T. Free electrons in the sheet will migrate towards the positive plate of the capacitor. Then, the metal sheet is attracted towards whichever capacitor plate is closest and gets stuck to it, so that its potential is the same as that of that plate. The gap between the capacitor plates is reduced to d, T so that the capacitance increases. Case 2, negligible thickness. The thin metal sheet divides the gap into two of thicknesses d1 and d2 of capacitances C1 equals epsilon 0 A d1 and C2 equals epsilon 0 A d2 in series. Exercises Q2.4, page 212. Answer in brief. The safest way to protect yourself from lightning is to be inside a car. Justify. Solution. There is a danger of lightning strikes during a thunderstorm. Because trees are taller than people and therefore closer to the clouds above, They are more likely to get hit by lightnings. Similarly, a person standing in an open ground is the tallest object and more likely to get hit by lightning. But a car with a metal body is an almost ideal Faraday cage. When a car is struck by lightning, the charge flows on the outside surface of the car to the ground, but the electric field inside remains zero. This leaves the passengers inside unharmed. Exercises Q2.5, page 212. Answer in brief. A spherical shell of radius b with charge q is expanded to a radius a. Find the work done by the electrical forces in the process. Solution. Consider a spherical conducting shell of radius r placed in a medium of permittivity epsilon. The mechanical force per unit area on the charged conductor is, where sigma is the surface charge density on the conductor. Given the charge on the spherical shell is q, sigma equals q, 4 pi r2. The force acts outward, normal to the surface. Suppose the force displaces a charged area element sigma ds through a small distance dx, then the work done by the force is. Exercises Q3, page 212. A dipole with its charges, q and plus q located at the points O, B, O and O, plus B, O, is present in a uniform electric field E. The equipotential surfaces of this field are planes parallel to the YZ plane. A. What is the direction of the electric field E? B. What torque would the dipole experience in this field? Solution. A. Given, the equipotentials of the external uniform electric field are planes parallel to the YZ plane, the electric field. Exercises Q4, page 213. Three charges, Q, plus Q, and Q are placed at equal distance on a straight line. If the potential energy of the system of the three charges is zero, then what is the ratio of Q? Q. Solution. The above figure, He line joining the charges is shown as the z-axis with the origin at the plus Q charge. Let Q1 equals plus Q and Q2 equals Q3 equals Q. Let the two Q charges be at A, O and A, 0, since the charges are given to be equidistant. Therefore R21 equals R31 equals A and R32 equals to A. The total potential energy of the system of three charges is. Exercises Q5, page 213. A capacitor has some dielectric between its plates and the capacitor is connected to a DC source. The battery is now disconnected and then the dielectric is removed. State whether the capacitance, the energy stored in it, the electric field, the charge stored, and voltage will increase, decrease, or remain constant. Solution. Exercises Q6, page 212. Find the ratio of the potential differences that must be applied across the parallel and series combination of two capacitors C1 and C2 with their capacitances in the ratio 1:2 so that the energy stored in the two cases becomes the same. Solution. Exercises Q7, page 213. Two charges of magnitudes -4q and +2q are located at points 2a, 0 and SA, 0, respectively. What is the electric flux due to these charges through a sphere of radius 4a with its center at the origin? Solution. Exercises Q8, page 213. A 6 microfarads capacitor is charged by a 300V battery. If the capacitor is disconnected from the battery and connected across another uncharged 3 microfarads capacitors, what is the energy lost in the form of heat and radiation? Solution. When two capacitors of capacitances C1 and C2 are connected in parallel, the equivalent capacitance C equals C1 plus C2 equals 6 plus 3 equals 9 microfarads. Equals 9 times 10 to 6 F. By conservation of charge, Q equals 1.8 C. Exercises Q9, page 213. 125 small liquid drops, each carrying a charge of 0.5 microcoulombs and of diameter 0.1 meters form a bigger drop. Calculate the potential at the surface of the bigger drop. Solution. N equals 125, Q equals 0.5 x 10 to 6 C, D equals 0.1 meters. The radius of each small drop, R equals D, 2 equals 0.05 meters. The volume of the larger drop being equal to the volume of the n smaller drops, the radius of the larger drop is. Exercises Q10, page 213. The dipole moment of a water molecule is 6.3 x 10 to 30 cm. A sample of water contains 1021 molecules, whose dipole moments are all oriented in an electric field of strength 2.5 x 105 Nc. Calculate the work to be done to rotate the dipoles from their initial orientation θ1 equals 0 degrees to 1 in which all the dipoles are perpendicular to the field, θ2 equals 90 degrees. Solution. P equals 6.3 x 10 to 30 cm. N equals 1021 molecules, E equals 2.5 x 105 Nc, θ0 equals θ1 equals 0 degrees, θ equals θ2 equals 90 degrees. W equals P cos θ0 cos θ. The total work required to orient n dipoles is W equals Np cos θ1 cos θ2 equals 1021, 6.3 times 10 to 30, 2.5 times 105 equals 15.75 times 10 to 4 J equals 1.575 millijoules. Exercises Q11, page 213. A charge 6 microcoulombs is placed at the origin and another charge 5 microcoulombs is placed on the y-axis at A equals 0, 6.0 meters. A. Calculate the net electric potential at P equals 8.0 meters, 0. B. Calculate the work done in bringing a proton from infinity to the point P. What is the significance of the negative sign? Solution. B. The electric potential V at the point P is the negative of the work done per unit charge, by the electric field of the system of the charges Q1 and Q2 in bringing a test charge from infinity to that point. That is, in bringing the positively charged proton from a point of lower potential to a point of higher potential, the work done by the electric field on it is negative, which means that an external agent must bring the proton against the electric field of the system of the two source charges. Exercises Q12, page 213. In a parallel plate capacitor with air between the plates, each plate has an area of 6 x 10 to 3 m2 and the separation between the plates is 2 mm. A. Calculate the capacitance of the capacitor. B. If this capacitor is connected to 100 V supply, what would be the charge on each plate? C. How would charge on the plates be affected if a 2 mm thick mica sheet of K equals 6 is inserted between the plates while the voltage supply remains connected? Solution. C. The dielectric of relative permittivity K1 completely fills the space between the plates, because T equals D, so that the new capacitance is C equals K1 C0. With the supply still connected, V remains the same. Therefore Q equals CV equals KC0 volts equals KQ0 equals 2.655 nanofarads equals 15.93 nanocoulombs. Therefore, the charge on the plates increases. Exercises Q13, page 213. Find the equivalent capacitance between P and Q in the following diagram. The area of each plate is A and the separation between plates is D. Solution. I. The capacitor in the first diagram is a series combination of three capacitors of plate separations D3 and plate areas A, with C1 filled with air K1 equals 1, C2 filled with a dielectric of K2 equals 3, and C3 filled with a dielectric of K3 equals 6. E. The above second figure, a series combination of two capacitors C2 K2 equals 3, and C3 K3 equals 6, of plate areas A2 and plate separations D2, is in parallel with a capacitor C1 K1 equals 4, of plate area A2 and plate separation D.